when I do a regression analysis in Excel, I get a whole bunch of additional stuff. I get, for example, with our studying versus exam grades data that we had here, number of hours spent studying versus the exam score, we see that we got a regression equation. We looked at the scatter plot last time. Grades should go up about 2% for every additional hour studied. If we didn't study at all, we should earn about a 49.5. Those are our coefficients here. We can get an R value for this. If I go to my trend line, I can format it and ask it for the R squared. And that tells me that about 40% of the variation in grade is directly related to the amount of time spent studying. That's our coefficient of determination. That means that the other 60.5% are other factors. But when I do the regression analysis in Excel, I get all of this. I get my R squared right there, 39.4%. There's my correlation value using the correlation function in Excel. But I also get this entire ANOVA. What is this ANOVA? We're looking at variation, right? That's a single factor ANOVA. And the factor here is the variation caused by hours spent studying. So we're trying to explain the variance in Y around its mean using the standard ANOVA techniques we did. And we don't get an actual F critical in the automatically generated ANOVA. I had to look it up automatically by doing the F inverse for 95%, our alpha being 0.05, sorry. But I don't really need it because right here is the significance of the F value. Significance of F, that's a p-value. That's the p-value I want to use to determine, is this a good fit? Should I reject the null hypothesis that my assumption is? What is my assumption for a regression? It's the assumption I was using for a regression previously. Mentioned this on Monday.
I think it was like no slope.
My slope should be 0. If I reject the null hypothesis, then I would say, hey, there is a correlative factor. The slope should be non-zero. My threshold is 5%. That's 5.2. It's really close to the edge here. Maybe I would say it's marginally significant, but it really is telling me that you can study all you want here. The effect it has that I can directly attribute to studying on your exam grade isn't all that great for whatever this set of data was. And if I look at the confidence interval for that X variable, that's this row here, I notice that that confidence interval contains 0. Negative 0.02 to 3.94. Since it contains 0, I can't reject this null hypothesis. That's in line with the p-value of 0.52. Notice that the calculated F is 5.2 and the critical F is 5.3. I'm not in the rejection zone. I'm still in that unshaded area. So all three of these items together tell me, no, this doesn't work. This isn't statistically significant. All right. This example in and of itself, I'd already done all the work, so I'm not sure it was as helpful as it could be. Let's go back and do one from scratch. Here, it's problem 31. Problem 31 says, do the number of orders I have from a particular company relate to the shipping costs for that company? Let's determine if there's correlation here. If I order more things, do my shipping costs go up? I'll start with a scatter plot. Insert scatter plot. What do you think just from looking at it off the very top of your head? As the number of things I order go up, does my cost of shipping go up? Kind of looks like it. Positive relationship. It's not very tight, but it sure as heck does seem to have a trend that as I go from left to right, we are going up. Well, let's get a closer look. I go to the data, I right click that, and I ask it, add a trend line, which it will then allow me to, got to go back and highlight the trend line. I hit the wrong thing. Format trend line. Go down here, I can get the equation. I can get the R squared value, that coefficient of determination. So, just looking at this information. Per additional order, what is my increase in cost? Assuming these are all in dollars and individual units, yeah, per additional unit, I spend another $5. Negative 31.2, what does that mean? What does that intercept represent?
Like, if you had no orders, you'd be losing, like, or the shipping costs would be like -31, which would make sense.
Right. So in this case, that's not a useful piece of information. If I didn't have any orders, the shipping company owes me $31. Not gonna happen. Okay. R squared is 0.6717. Means what? Aha. So there's some other factor, about 33% of it is due to forces outside of just the number of orders. It might be, where am I ordering from? Where am I having it delivered to? It might be shipping line fluctuations that are seasonal because it's closer to Christmas or closer to midsummer or whatever weather issues might come up. There are other factors that cause variation in the shipping costs. Okay. Let's actually, said I did this before, but there it is, the same stuff. Let's actually run the data analysis. So let me close this trend line stuff, move that a little further over. I go up to data. I go to data analysis, which is over here on the right. And I do regression. Now, again, remember when I do the regression, Y range goes first. Then X range. I'm going to say I want the confidence at 95%. I'm going to ask it for just do the analysis. Put it in a new sheet. Oop. I forgot to check the labels box. I told it that I had included the labels, orders, and shipping costs. I need to check the labels box. Okay, bunch of stuff. So there's my R squared, 0.6717. Second line in regression statistics. Underneath that, notice though, it says adjusted R squared. There's a way to adjust this R squared, which I haven't talked about yet, so I'll get to that in a little bit. I've got the standard error, and then I've got all of the ANOVA results down here. Let's take a look at the confidence interval for our X value. That's down here in the bottom row, all the way on the right. The last two numbers on the right are the lower 95%, upper 95%. Those are the edges of my confidence interval. So I am 95% sure that the slope should be, sorry, the slope, because that would be the coefficient for the x, the slope should be between 2.5 and 7.36. Based on that number alone, that confidence interval, what should I be able to say about my null hypothesis? The null hypothesis would be that the slope is 0, that confidence interval. It doesn't include 0, so I would hope that this null hypothesis is rejected. Where can I look to find out if the null hypothesis is rejected? And there's a p-value for that slope right here. It's in the p-value right on that row, but it's also up here in the significance of our f-test. Notice those are the same number. 0.0011 is way smaller than 0.05. That says reject the null hypothesis. It's too small. Out we go. One of my former students is now teaching statistics in West Virginia. And instead of H sub 0, the null hypothesis, she reads it as HO. And she said this to her AP stats group because their test for AP statistics was earlier this week. When the HO is low, reject it. When the P is low, reject a HO. Well, there you go. My p-value is really small. I reject my null hypothesis. Okay, my confidence interval doesn't contain it. My p-value is really small. I have a very large f. I would be in that rejection zone. I'm going to say we're out. So the larger our f value is, the better our line fits our data. The closer I am to understanding how well this ANOVA truly works. Questions?
Is this telling us the same thing as R squared? Because R squared is also telling like amount of variation, like attributable.
R squared gives me the amount of variation that's attributable to this cause. And the higher that is, I would expect the p-value and the f to be better. So they're very similar ideas. I could ask, I got this confidence interval for the slope. What does that look like? If I thought about this confidence interval, I could actually draw a confidence interval on my linear regression. Now, this is not something that Excel will do automatically. You can go through and do it manually, but there's my linear regression and there's my confidence interval up here. Notice that the closer we get to the center of the data, the narrower that confidence interval gets. Up here, we have something called a prediction interval. They're generated in two different ways. It's not automatic. There are ways to build these in. I just don't think they're as useful as we'd like them to be. They were much more useful in our ANOVA fashion. DTT. Questions? I'm not going to look at the prediction intervals and the confidence interval that much. What I am going to ask is about the assumptions we made. When we do an ordinary regression, we make the assumption that the error is normally distributed, that the average error has the same variation across all the different x values we gathered, and that the errors are independent of one another. So, how could I figure out if those assumptions are true? I can't really see the errors directly. But what I can figure out is the residuals. So what if instead of looking directly at error, I look at my residuals? What's a residual again? When we actually do a scatter plot, like we did for the data in our shipping cost idea, I can see the regression line, I can see the data themselves. The residual is
like the difference between the data and line.
exactly the vertical distance from each data point straight down to the line. So I can't draw those on here in Excel, but I could imagine each of these data points having a little stick from the dot to the line, make it look like a little lollipop, right? Some of them go up, some of them go down. This one, for this fourth data value, that's really small because that's actually touching the line. Up here at this sixth data value, that's pretty close. But this last data value all the way on the right, that's pretty far away from the line. That's going to have a big residual. So I can think of the residual as the difference between the actual Y value and our predicted Y value. And I believe in the textbook, we use the predicted Y value has a hat on it. I'm going to call this EI. And I'll get one for each value we collected. So in our spreadsheet that we were just looking at, we had 12 of these, so I'd have error 1 through error 12. So now that I have these numbers, I could say, how can I check these errors are normally distributed? How can I check if they have constant variance? How can I check to see if they're independent? I can do this by looking at the residuals themselves. Let's go back to our spreadsheet for a moment, and let's redo the regression analysis. So I'm gonna get rid of this sheet. Delete. Poof. I'm going to go back here and I'm going to say data analysis, regression. I'm going to tell it to use the shipping costs and the orders. But notice down in the bottom section where it says output options, there's a bunch of other stuff. And 4 of those options are about the residuals. All four of these right here are about residuals. And underneath there's something called a normal probability plot. So I want to look at these items. So let's go ahead and check all 5 of these boxes. And now when I run the regression, I'm going to get a bunch more stuff. Oh boy, there's a lot of stuff here. So if my errors are not normal, then the confidence interval might not be right. So let's look at the residuals. Here are my residuals. Down here, it shows residual output. And in each of these columns, I have the predicted Y value, and I have the actual Y values in the original data, so it computes the residual right here. So there are my residuals. Another column that says standard residuals. Standard residuals? Standard residuals. I did standardizing of data way back in descriptive statistics, back in chapter 4. We standardized stuff, we got z-scores. Our residual is data minus the predicted value. We did data minus average, right? This is like a z-score. These standardized residuals are parallel in idea to z-scores. Oh, so if I look at these instead, I should see those looking like z-scores. I need a histogram. I need a histogram of these, but I'm going to make my life easy. Let's just go by ones. So I want to plot these, but it did that over here. It plotted the regular residuals, right? As opposed to the standardized ones. Some were positive, some were negative. Let's plot these. Insert histogram. There's my histogram insert. That didn't work. I need to adjust my bins. Is there an easy way to adjust my bins from here? Having already done that? No, it's a pain in the neck to do it from there, so let's not. There we are, bins. Format data series. Bins. Bin width 1. Make a bin width of 1. Hey, look at this. All of my bins are between -1. All my residuals are between -1.4 and 1.7. Normal distribution means I should have very few outside -3 and very few outside +3, but I would expect more in the middle and further out toward the end, they would be less. I could make this bin smaller, 0.5. That shape doesn't really look like a normal distribution, does it? I only have a few values. Maybe it should look more like a T distribution. I would still expect more in the middle and further away. That wouldn't be helpful. Do I have outliers? I don't even have any unusual values, right? Because outliers are outside of -3 and +3, and unusual is outside of -2 or +2, and none of my values are bigger or smaller than 2 or -2, respectively. So I'm pretty sure this is okay in terms of the residuals. Get rid of that for the moment. Let's go back over to the charts they gave me. This chart right here, it's a little small, so let's move that to a separate page so we can see the whole thing. This shows a graph of the actual values in blue and the predicted values in red. This is very much our scatter plot, but instead of having the regression line, it's just got the dots so we can see the residuals a little more closely. Some of these residuals are fairly large, some of these residuals are fairly small. But I can actually say, hey, are there particularly large distances and particularly small distances? Again, this is not as useful to me as just the plot of the residuals that we saw up here. This, where's our normal probability plot? Where'd my normal probability plot go? I ate it. That's the fit line plot. There it is, normal probability plot. Let's make this a separate page as well. Move chart, separate sheet. Okay. The normal probability plot plots the residuals against a normal distribution. So we're expecting a normally distributed ID here. And I'm saying, well, if we were normally distributed, then I should have this many at this percentage and this many at this percentage. What I want to look at here is this a straight line? Roughly. The closer this is to a straight line, the more I can say, yes, this is a normal set of distributed residuals. The advantage here, this is pretty good for a straight line. I could actually find the regression on this, couldn't I? I could say, let's look at this data and add a trend line. And on that trend line, let's find an R value. Look at that. Look at that. It's kind of hard to read at the moment. Let me make the font bigger. Text options. Where's my font? Label options? Screw it. We'll just grab it and make it bigger. Should let me grab you. I'm grabbing the wrong thing there. Grab this. Let's blow it up this way. Look at that R value. R squared is 0.97. That's really close to 1, isn't it? Yeah, this is normally distributed. So I have the ability to check normal distribution of the residuals using this normal probability plot. I think that's the most useful piece of it. How do I determine whether or not the variation is the same? Because that was condition 2, that the errors have the same variance. Well, if I'm looking at variance, I'm looking at whether or not there's some change in the residuals based on our X itself. In other words, as my graph goes from left to right, does the variation in the residuals get bigger or smaller, or does it keep getting random looking? Let's go back and look at our data. Here, way back up at the top, is our actual residual plot. I'm going to make this a separate page for the moment. Move chart to a separate sheet. Bang. Okay, so here's a question for you. As we move from left to right, do you see the data get further apart or closer together? Or does it kind of look like it's the same width all the way across? In the textbook, at the top of page 488, we have pictures with more data. So I will come back to this picture in a second, but let's look at the pictures in the textbook for the moment. Here are three pictures. On the left, I've got the data doesn't seem to get closer together as we go from left to right. Doesn't seem to get further apart as we go from left. That's this one. But in the middle, there's a clear spread as we go from left to right. And in the right picture, there's a clear narrowing as we go from left to right. So I can say that in the middle and the picture on the right, the data's variance, the residual, changes with X. The residuals are getting bigger as X gets bigger. The residuals are getting smaller as X gets bigger. That means that the variance changes from one end to the other. That's a problem. We're going to call this condition, and I hate this word, heteroscedasticity. Written right here at the top. This is heteroscedastic data. You got to be kidding me. I'm never going to use that word again. It's data that's funneling out. And on the right picture, it's funneling in. In the left picture, it's not funneling in either direction. It's the same across. We would call it homoscedastic. I've never heard these terms used outside this textbook. They are the formal terms in statistics. Never heard them used. But I can now say, okay, if I see a pattern where things are getting bigger or things are getting smaller in my residuals, I can then say, oh, the variance is changing as X changes. Let's go back to this picture. There isn't a lot of data here. But do you think the variances are bigger on the right side than they are on the left side? I see the widest variation over here on the right. These points are pretty high up, but these points over here on the left are pretty close in. I might actually say, no, I think this is not the same variance, but there are also a very small number of data points. There are only 12 data points. It's much harder to do this on smaller data sets. But again, I could say, okay, maybe the variance is not the same here. I would need to worry about that. So this is a visual description only. But notice it needs residuals to figure it out. I need to have all the residuals I can have to get this. Questions? So for normal distribution, I look at that normal plot, or they sometimes call it the QQ plot, quintile plot. But the Excel calls it that normal probability plot. That was this one. For the idea of constant variance, I look at the residual plot itself. What was our third possible assumption? The errors were normally distributed. The errors were the same everywhere in variance. Oh, they were independent. Now, how do I know whether or not these are independent or not? Okay. Independence is actually asking me, is there some error that happens with regularity, some change in the error? Like the first error is positive, the second error is negative, the third error is positive. Maybe it keeps flipping signs. Maybe there's some sort of seasonal effect in there. And I get this sort of trig-looking graph, this wave going on. That's not going to be something that's apparent here because we're only looking at order size versus the residual. But if I was looking at something that had sign changes, I could look at the sign changes in my residuals. And I could say, hey, look, Are we flipping back and forth with any regularity here? As X gets bigger, our observations are numbered in order from left to right. Are the residuals ordered somehow? Is there some relation between this first and second, and the second and the third, and the third and the fourth? If it flipped back and forth every time, we'd call that a first order autocorrelation, correlation between the residuals themselves. If we had maybe every two going back and forth, we'd call it a second order autocorrelation. If we have very few changes, we say that's a positive autocorrelation. If we have lots of changes, we call it a negative autocorrelation. It is harder to determine whether or not there is a problem with independence when I have negative autocorrelation. Let me go back to the picture in the textbook here. Here are autocorrelations for 50 pieces of data. Over there on the left, we don't change sign very often. It's only 11 sign changes back there. But over here on the right, we changed 36 times out of 50 data values. There might very well be something going on here because of how regular those peaks and valleys appear to be. I might be able to say, hey, there's something going on relating the data back to itself. And that's why we use the phrase autocorrelation. A lot of things are positively autocorrelated, where we have very few sign changes, but there's some sort of cyclical wall pattern. Negative autocorrelation is not common and therefore should be remarked upon. Let me do another example from scratch. Close this here. This example is about cockpit noise. In an aircraft, we have sound levels, and we're going to measure the cockpit noise. So, I did the regression analysis here. Is there a relationship between airspeed, how fast the plane is moving, and the noise in the cockpit? It's a yes or no question. Is there a relationship? What up here is going to tell me that?
Putting it against F and the p-value for like the X.
Exactly. The two p-values. The p-value for the significance of F and the p-value for the X variable. And those are the same number. 1.595 times 10 to the negative 30th. That is a teeny tiny, itty bitty number. That's basically zero. What do? What does that number tell me to do? P-value is very, very small. Which means
the slope isn't zero.
Which means there is a relationship. The relationship says, hey, as we get faster, noise goes up by 0.07 decibels per whatever the unit of airspeed is here. I believe it's knots. Yes. So the faster we're going, the louder it's getting. Great. Let's look at our residuals. Lots and lots and lots of residuals. And there's the column for the percentiles here. That's our normal probability plot piece. And I actually told it to do all the plots, and I put them on separate pages already. So here's my normal probability plot. Tell me, Do you think we have a normally distributed set of errors? That kind of look like a line. It's not a great line because they're all dotted all over the place, but if I were to grab this and say add a trend line, it's not that far off from a line, is it? Okay, I'll buy that. That's mostly normally distributed. Good enough for me. I can look at the line fit plot, but that's not as helpful as the normal probability plot, in my opinion. Let's look at the residuals. Here's the residuals themselves. The residual plot. Are these residuals getting smaller as we go from left to right, or bigger as we go from left to right, or do they seem to stay the same as we go from left to right? Which means I would say that there's no violation of my not independence, of my the second one. Errors are normally distributed. I've lost my plot. Go back and look at the list. The errors have constant variance. It's not getting smaller, it's not getting bigger as we go from left to right. They're not changing with X. So that's what that tells me. And then the question of independence would come by looking at sign changes. So let's figure out how to change this plot so I can count sign changes. How could I change this plot to add the ability to know where are the sign changes? I could connect the dots. If I connected the dots, I'd be able to see something, wouldn't I? In order, we see a lot of sign changes. Maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But they're not with any regularity, are they? This doesn't seem to be highly autocorrelated. I'm going to say that this is okay. So I have the ability to make these judgments visually. I can also ask two other questions. Are any of these residuals, let me go back to the residuals themselves, are any of these residuals unusual or outliers? How would I figure that out? So I need to go to the standard residuals, and I need to look for numbers there that are out of line, like bigger than 3 or smaller than -3 for outliers, bigger than 2, smaller than -2 for unusual, excuse me. So as I start scanning, I get close to -2. Oh, there's one right there. That's an unusual data value. I'll highlight it for the moment so we can come back to it. There's another one. So it looks like I only have 2 unusual data values, and they're just barely outside of 2. They're both high. Okay. With that information, I could then say, I wonder if those particular values are causing the trend line to look different. I didn't actually draw the trend line. Let's draw the trend line. Insert scatter plot. Trend line. Make this a separate page for the moment. Move chart, new sheet. Okay. I could ask, is there a point on this data that is far enough away from the other data points or far enough away that it would give me something way outside the average in X and the average in Y? This is best described visually. If all of the data is fairly clustered together, and then there's this one oddball point out on either edge, I would call that a point with high leverage. In this case, it doesn't look like there are a lot of points that are significantly spread out from the central clustering. So I could say, no, I don't think there are high leverage behaviors here. Take a look on page 493. Here is a scatter plot. And this point right here, here's the average of the X's. And this point is way out, isn't it? That's got a lot of pull because it's so far away. This one's the farthest away from the mean in the other direction. This one is much further. We could actually calculate the leverage. It's a pain in the neck. I don't want to do it. But if I calculate the leverage, when my leverage is above 4, we tend to say, all right, this is a high leverage point. So that's measuring something that's influential. Sorry, not 4, 4 over the number of observations, 4 over n. But I can best describe this visually. I've got this one dot. If I move this even a little bit up or down, it would change that line a lot because of how far out it is. It's an influencer on the rest of the data. Since a lot of this is done visually, me asking you to do it from scratch, calculate it all during the exam is a pain in the neck. I would instead say, okay, here's the picture. What can you tell me about it? Here's the information. Here's the residual plot. Here's the list of residuals. Are any of them unusual or any of them outliers? I would have to give you the information we got in our Excel spreadsheet. So you'd have to get something like this plot, or you'd have to get something like the list of residuals, or something like the normal probability plot for us to answer questions about. So you will not have to do the regression. You won't have to actually do all the calculations, but you'll get them, just like we did for the F-test. Hey, here's the ANOVA result. The F-test result for comparisons of variance. Tell me what it means. Questions? Next semester, when you take quantitative business methods, we're going to say, okay, I now have things that are influenced by more than one thing. Remember, we said when we looked at that coefficient of determination that a certain percentage was attributable to the thing we were looking at, the response and the predictor. The predictor says this much about the response. What if there are multiple predictors? How do I take that into account? That's for next semester, but it's based off of this idea. And look at how much we had to build to get here. To do regression, we had to do ANOVA. We had to do standard errors and standard and confidence intervals. And all of the stuff we were doing for the last 5 chapters comes together here. And the purpose is for you to make better decisions with real information about the situation. So that's all I'm going to ask you for chapter 12. And that means that's the last piece of homework I'm going to want from you. And our last class is Monday. So guess when you get to turn that homework in. If you have questions about that, you should be emailing me all through this weekend. If I only had power back after this crazy storm, so I can answer your emails. And if you've got questions, come talk to me. On Monday, I will answer any question you want about the final. I will see you then. Have a wonderful rest of your day. Enjoy your weekend.